Good afternoon. I'm Dan Freed, director of the Harvard CMSA. We're a center on campus that's engaged in mathematics, in two-way interaction with a lot of different science. You can find out a lot more about what we do on our website. And that science today is computer science. So this is the annual Yip lecture. We're very grateful to Dr. Yip for the funding for this lecture. And we're very pleased to have Scott Aaronson. Scott is an expert on computational complexity, quantum computation, AI alignment, many topics. And he's a professor at the University of Texas at Austin. And today he'll tell us how much math is knowable.
Okay, can you hear? Yep. All right, good. So thank you so much to Dan, who was my former colleague at UT Austin, but you know, Harvard is good too. It would be an honor, obviously, like on any week, to deliver the Yip lecture at Harvard, okay? But it's particularly an honor to speak at Harvard this week. You know, I mean, I think the rest of us in American academia are looking to Harvard right now to defend the value of their enterprise. So, you know, fight fiercely, Harvard. But, you know, the truth is that, like, the more depressing, you know, the news is and the more is happening, like, the more my own thoughts turn to things like the knowability of mathematical truth. Maybe I'm weird that way, okay? But, you know, the same questions that would have bothered, you know, Euclid or Archimedes or, you know, actually, so here is Archimedes drawing his circles in the sand, you know, with the cosmos behind him, at least as imagined by GPT-4o. Okay. So the starting point for this talk is an observation that I think bridges math and computer science and physics and philosophy. Okay, and it's simply that, you know, even if mathematical truth is timeless, is Platonic, is eternal, our ability to know mathematical truths is inherently limited by our own nature as finite beings, you know, in space and time, who are governed by the laws of physics. Okay, to illustrate that point, you know, I hereby present to you Zeno's finite time Goldbach decider. Okay, so Goldbach's conjecture, of course, is the statement that every even number, 4 or higher, is a sum of 2 prime numbers, right? It has been checked out to many trillions, certainly seems to be true, but after 300 years, there is still no proof of that statement, okay? But nevertheless, here is how we could easily learn the truth or falsehood of Goldbach's conjecture in only 2 seconds if we lived in a universe governed by different physical laws. Okay, so we would simply build a machine that, you know, in its first second would calculate that 4 equals 2 plus 2, and in the next half a second would calculate that 6 is 3 plus 3. In the next quarter of a second, it would calculate that 8 is 5 plus 3, 10 is, well, actually 5 plus 5 or 7 plus 3, and so forth, so that after 2 seconds, it would have checked all the whole infinity of cases and, you know, would tell us if Goldbach's conjecture is true or false. Okay, so, you know, you might say, well, this is silly. You know, of course we can't do this, but why can't we do it, right? And I think it's, you know, one cannot answer that question a priori, you know, sitting in one's armchair. One has to say something about the laws of physics of our world. Okay, and you know, if you're actually interested to know, as far as current physics can say, the thing that goes wrong, I don't mean at an engineering level, but at a fundamental level, happens once you're trying to do like 1 computational step per Planck time. Okay, a Planck time is about 10 to the minus 43 seconds. Okay, and what happens at a Planck time? Okay, what happens is that to do a step, even just like a photon bouncing from one place to another, then requires so much energy that your photon or your other apparatus that you're using exceeds its own Schwarzschild radius. What does that mean? It means that your machine collapses to a black hole. Okay, I've always liked that as nature's way of telling you not to try something. Okay, but of course, since the time of the ancient Greeks, we have had a technology for making statements, about a whole infinity of cases, as one usually wants to do in math, despite being finite beings. Okay, and that technology is called proofs. Okay, for thousands of years, people understood proof at an informal level. Okay, starting in the late 19th century with Frege, Hilbert, Bertrand Russell, and Whitehead, Peano, Zermelo, and Frankel, we actually made the notion of proof itself mathematical. And we learned how a purported proof of a theorem could be checked in a completely mechanical way. Okay, not all of these people would have put it this way, but today we would say any purported proof of a theorem can in principle be written in a format where it can simply be checked by a computer. Okay, it's just a string of symbols, with a fixed set of logical deduction rules that are allowed, a set of axioms that you start with, and checking the proof just means checking that each statement follows from the previous ones by one of the allowed deduction rules. Okay, so here is the page in Russell and Whitehead's Principia Mathematica, where famously, after developing several hundred pages of preliminary results, they are finally ready to prove the formal statement that corresponds to 1 + 1 = 2. Okay, and then they say it's occasionally useful. Okay, but you could say that what they were really doing is something that we would recognize today as coding. It's just that they were doing it in like 1910 before there were actual machines that could have automated and saved them many years of work. Okay, here is a proof of a conjecture in Boolean algebra called the Robbins conjecture, okay, which was one of the favorite open problems of Alfred Tarski for like half a century. Okay, and this conjecture was finally proven only in 1996 by an automated theorem proving program called Otter. Okay, and this is the proof. As you can see, it fits on one slide. I hope you find it illuminating to read. Okay, I mean, it's not like the color theorem, right, which was proved by a computer, but only by enumerating thousands of cases. In this case, the proof is actually quite short. A human can check it. Okay, it's just that empirically, no human was able to find this sequence of manipulations. Okay, and this is actually a feat of automated theorem proving that has not been equaled again, even in the modern age of LLMs. Okay, although maybe it will be soon. Okay, that is certainly a thing many of us are looking at. Okay, okay, but we also know famously from a century ago that this technology of proofs has inherent limits. Okay, so this brings us to Gödel and his famous incompleteness theorem. Okay, and there's this idea that the proof of Gödel's theorem is somehow complicated, or involves all kinds of number theory, blah blah blah. No, I can show you the proof on one slide. Okay, Gödel sort of had to work hard to prove this theorem, but the only reason for that was that the concept of a computer program had not yet been invented. Okay, it wouldn't be invented for another 5 years when Church and Turing did that, okay? And so Gödel had to sort of jury rig his own, concept of programming just for the purpose of this theorem. But, from a modern computer science standpoint, this is a one-slide proof, okay? So how do we prove incompleteness? We say take any formal system. So any system for, proving theorems from axioms by given deduction rules. An example would be the standard axioms of set theory, of all of math really for the past century, which are called ZFC, Zermelo-Fraenkel with the axiom of choice. Okay, but the details won't be important. Okay, this could be any axiomatic system in which purported proofs can be checked by a computer. Okay, and then what we do is we enumerate every possible sentence, every possible mathematical statement that you could have in that theory. Okay, each statement is just some finite string of symbols, okay, or ultimately a string of bits, if you like. That's how we think of it. And we are interested here in statements that take one integer parameter that I'll call n. Okay, so for example, maybe the 42nd statement, S42, on input n, will be the statement that the Fermat equation, x to the n plus y to the n equals z to the n, has no non-trivial integer solutions. Okay, so then there is one such statement for each n. Okay, and then we construct a new mathematical sentence, which I'll call phi f of n, and what it says is that Sn, so the nth statement, on input n, so you notice the same n appears twice, that statement has no proof in f. Okay, or in other words, if you write a computer program to enumerate all of the possible strings, then that program will reject every string. None of them will be a valid proof of Sn of n. Okay, so that is simply a statement that a certain computer program runs forever, and so it is clearly a mathematical statement, even a very concrete statement of arithmetic. Okay, and then the next thing you do is that you make a new sentence, gf, which is just phi f, where I give it as the input n, I give it the number of phi f itself in this list. Okay, the number at which it appears. And then if you think about that, that gives us a sentence that says, I, myself, this sentence, have no proof in f. Okay, so it asserts its own unprovability. And then, well, there's two cases. That statement is either true or false. Okay, but if it's false, then it does have a proof. Okay, and so then there's a proof of something false. So the axiomatic theory is unsound. If the statement is true, on the other hand, then it's true that it has no proof, and so therefore our system is incomplete. There's a true statement that's unprovable, even a purely arithmetical one. Okay, and if you've heard of the second incompleteness theorem, that is just the statement that this G of f, I am unprovable sentence, is equivalent to the consistency of f, the statement that you cannot in f prove a contradiction like 0 equals 1, because if f is consistent, then G of f is true. If f is inconsistent, then it's not true because f can prove anything. Okay, and furthermore, that equivalence can be proved in f itself. So, so what you get is that if f is a sound theory, then it cannot prove its own consistency. Okay, ironically, you can have an unsound theory that proves its own inconsistency and that is consistent. Okay, but it can't prove its own consistency and be consistent. It's like the people who brag the most are the ones with nothing to brag about, right? Okay, but now a key question ever since Gödel has been how pervasive is this incompleteness phenomenon, right? Will we just bump into it all over the place? Like, does this explain why there are so many unsolved math problems? Is it just because these are Gödelian statements with no proofs or disproofs? Well, I think the truth of the matter is that since 1931, independence from strong formal systems has reared its head much less often than you might have feared that it would at the time. Okay, and in a sense, this is good news, right? I mean, imagine if Andrew Wiles, when trying to prove Fermat's last theorem, or Grisha Perelman, when proving the Poincare trying to prove the Poincare conjecture had just given up, said, it's probably another of these, Gödel sentences that just has no proof or disproof. Okay, I guess, lucky for all of us that they didn't, right? Okay, the most compelling examples of independence, I would say all come from set theory. The most famous example being the continuum hypothesis, which is the statement that there is no infinity of intermediate size, okay, between the infinity of the integers, called Aleph 0, and the greater infinity of the real numbers, which we call the continuum, or 2 to the Aleph 0. Okay, so famous work by Gödel and by Paul Cohen established that the continuum hypothesis can neither be proved nor disproved from the ZFC axioms of set theory. Okay, so in other words, if those axioms are consistent, then either answer can be added to those axioms without producing any inconsistency. Okay, so from one point of view, this is a real example. It's a question that people cared about. And the answer is, it is one of these independent things, okay? But, I think only some people would regard that as a real example of an unknowable mathematical truth. I think many others, probably including me, would regard it as, well, we have simply learned that the truth of the matter is that there is a multiverse of different possible set theories. Okay, there are set theoretic universes where the continuum hypothesis holds. There are others where it doesn't hold. And, that is, arguably the most that we're ever going to know, right? At least, if we don't want to argue about, new axioms. So, with statements of arithmetic, okay, which includes, Goldbach's conjecture, but also includes, most of the other things that we deal with in math, the Riemann hypothesis, P versus NP, can all be ultimately phrased as statements of arithmetic. There, we don't really have the same option of just saying there's a multiverse and be done with, and just being done with it. Okay, because like if I have a computer program, I think I know what it means to say that that program halts or that program runs forever. Right? If someone tells me, well, it halts in one axiom system and runs forever, in a different axiom system, then my immediate response will be to say, well, then screw your axiom systems, right? I just want to know what it actually does. It clearly does one thing. Okay, so I do think that arithmetical statements are fundamentally different in that regard. Okay, of course, Gödel's theorem is so striking precisely because it does apply to arithmetical statements, although not ones whose truth, we're really in that much serious doubt about. Okay, so I want to return to this theme of the pervasiveness of the Gödel phenomenon, and and like how soon, how quickly, as we explore math, does independence rear its head. But there's one other ingredient that I need before we do that, which is Turing's theorem. Okay, so the closely related concept of uncomputability. Okay, and once again, this is a one-slide proof. Really a half-slide proof. Okay, so here is the famous thing that Alan Turing did as a 22-year-old undergraduate in 1934. No pressure to any of you. Okay, which basically launched the field of computer science. Okay, he defined this notion of a Turing machine, which today we would simply call a computer, universal computer. It's a an idealized mathematical model of what a computer is, what a program is. And then he proved that these programs have limitations. In particular, there is no program that can take as input some arbitrary other program and then decide whether it halts. Okay, well, what's the proof? Let P be such a program. Okay, so it takes as input another program M, and it tells you whether M halts or runs forever when M is run on a blank input. Okay, then it is easy to see that we can use P to create a new program that I'll call Q, okay, which takes as input a program M and now runs M on itself as input, runs M on its own description as input, and then if M halts on its own code, then Q will run forever, whereas if M runs forever, given its own code, then Q will halt. So it does the opposite of whatever M of M does. Okay, this may look familiar from Gödel, right? And now, comes the twisting the knife step, okay? Where we give Q its own code as input, okay? So we give, we run Q on Q, and if it halts, then it has to run forever. If it runs forever, then it has to halt, okay? Okay, so, the only conclusion is that Q can't have existed, therefore P can't have existed either. Okay, and by the way, once we know Turing's theorem, then we can immediately deduce a version of Gödel's theorem as a corollary, right? We simply say, well, suppose that we had a complete and sound proof system for arithmetic, then, given any program, we could decide whether that program halted by simply enumerating every possible proof and disproof that program halts or runs forever, and eventually we'll find one, right? But that would solve the halting problem, which we already proved was impossible, okay? Therefore, there can't be such a proof system. Okay, so now I get to show you, my personal, favorite function, okay, since I learned about it as a teenager, and it, amazed me then and still does now, and I'm proud to say that, my kids are very into this function as well now, okay, but it's called the Busy Beaver function, defined by Tibor Rado in 1962, and it makes the concepts of uncomputability and incompleteness concrete, vivid, like nothing else that I know about. Okay, so here is a Turing machine. Let's see if this animation will work. This is from Quanta magazine. It had a really beautiful animation of a Turing machine from an article about the Busy Beaver function. Okay, so this is what a Turing machine looks like. It just has an infinite tape, divided into the squares on which zeros and ones can be written. And then it has a finite state control. Okay, so the machine has some internal state, and the state decides what to do. And the things you can do are look at the current symbol. Depending on what the current symbol is, you can either leave it how it was, or you can overwrite it with a 0 or a 1, and then you can move one square to the left or one square to the right, and you can halt. Okay, and that's it. Okay, so in some sense, once you know those rules, then in principle, you can make Linux, you can make Windows, you can make Minecraft, any other software that you want. It's just all the programming languages can be compiled down into this. Okay. Okay, so now what is the Busy Beaver function? So, we could define it with any programming language, but we're going to define it in terms of Turing machines just to make things perfectly concrete. Okay, so did we say Busy Beaver of n? The nth value of this function is going to be the maximum finite number of steps that any n-state Turing machine can make on an initially blank input before halting. Okay, so the number of states in the Turing machine is like the number of lines in a computer program, right? It's like a measure of the complexity of that Turing machine. It's the length of its description. Okay, so we look at all the n-state Turing machines, of which there is an exponential in n, but still finite number. Okay, and some of those machines run forever. They just go into an infinite loop, or they go off, all the way forever to the left end or to the right end of the tape, or something more complicated. Okay, those machines that run forever, we just throw them all out. We consider only those n-state machines that initially halt. Sorry, that eventually halt when given the all zero initial tape. Okay, and each of those machines runs for some finite number of steps. We take the largest of those numbers. That is Busy Beaver of n. Okay. And now the key point about this Busy Beaver function is that it is a very concrete function which nevertheless grows faster than any computable function. Okay, how can we see that? I'm actually going to give you two proofs on one slide. Okay, so proof number one is, let's suppose we had a function f that was computable and that exceeded Busy Beaver of n, so it upper bounded it. Okay, well then we could use that f to solve the halting problem. Right, if you give me a Turing machine with n states, I will just calculate f of n, and then I will run that machine for f of n steps, and I'll see if it's halted by then. If it hasn't, then by the definition of Busy Beaver, I know that it never can halt. has to run forever. So either way, I've solved the halting problem. Okay, so that shows us that there can be no computable function that dominates Busy Beaver, right? But let's actually prove a stronger statement, which is that Busy Beaver dominates every computable function. Okay, so to prove that, say let's let f be a function that is computable. If it's computable, there's some program that computes it called a program P. So P takes n as input, computes f of n. Okay, then it's not hard to build a Turing machine that's going to have this number of states. So like we have however many states are in P plus log of n, because we need to hard code n itself, you know, in binary, let's say, plus some small number of additional states. So at any rate, a number of states that is going to be much less than n as n gets large. Okay, and what's this program going to do? Well, it's going to first use P on n to calculate f of n. Okay, and then once it knows f of n, it's going to run for f of n squared steps and then halt. Okay, so hence we have a program with less than n steps, and it runs for more than with less than f of less than n steps, and it runs for more than f of n steps. Okay, hence Busy Beaver has to has to include that machine and therefore dominate f. Okay, so now comes the fun part. What can we say about the actual values of this Busy Beaver function? Well, this has been a game in computer science for more than 60 years now. Okay, Busy Beaver of 1. What's the largest finite number of things that a one-state Turing machine can do? Well, a one-state Turing machine, either it just writes 1, go to the left, write 1, go to the left, write 1, go to the left, and then it does that forever, or it halts in the very first step. Okay, so Busy Beaver of 1 is 1. Okay, easy. Busy Beaver of 2, this can be given as a homework exercise. Okay, it turns out that it's 6. Okay, and this was proven by Shen Lin, who was Rado's student. Busy Beaver of 3, now this one was actually Shen Lin's PhD thesis. Okay, this one was harder. There were many cases to enumerate, and the trouble is, that like you can find a 3-state machine that runs for 21 steps, which and then halts, which he did. But once you do that, you're not done. Okay, because he had to prove that all the machines that run for more than 21 steps with 3 states actually run forever. Right? And then, you have to, he sort of had to do that on a case-by-case basis, right? Because the halting problem is uncomputable. Thank you, Mr. Turing. Okay, there's no general systematic way to do that. Okay, so he had to do it machine by machine. Busy Beaver 4 took another 2 decades to do. Okay, but there was a hobbyist named Alan Brady who just plugged away and away at it and eventually was able to prove that Busy Beaver of 4 was 107. Okay, now Busy Beaver of 5, for almost the entire time I've been in computer science, from a teenager to last year, all we knew was that Busy Beaver of 5 is at least 47,176,870. We had a 5-state machine that runs for that number of steps, and that seemed like the winner, but we couldn't prove that that all the other machines actually run forever, right? Like 5 years ago, right as COVID was starting, actually, I wrote, my COVID project was to write a survey article on Busy Beaver. Okay, and I'm very proud that this survey article spurred an international team to revisit the Busy Beaver 5 problem and finally solve it. Okay, and not only solve it, but actually generate completely machine checkable formal proofs that we now know that Busy Beaver of 5 is equal to 47,176,870. Okay, this was a major effort. I can take no credit other than to have inspired it, I guess. Busy Beaver of 6. So we don't know it. We do know that it is at least 10 to the 10 to the 10 to the and so on 15 times. Okay, it may be much, much bigger than that. Okay, don't ask me, Busy Beaver of 7. Okay, so now it might be interesting to look at what does the 5-state Busy Beaver do. right? Like what does it actually do that allows it to run for 47 million steps and then halts? It turns out that you can actually like decompile it. You can interpret what it is doing as checking a certain statement of, in number theory, in elementary number theory. Okay, so here is what it does. Okay, so let's define a function, an integer function, a g of x. Okay, and if x is a multiple of 3, then g of x is 5x plus 18 over 3. If x equals 1 mod 3, then g of x is this other thing, 5x plus 22 over 3. And if x is 2 mod 3, then g of x is going to be a special value that you could think of as the halt value. Okay? And so now let's ask the following question. Starting from 0, if I just keep iterating this function, applying it over and over, do I ever get to the halt state? Okay, well, I'm going to break the suspense. The answer is yes, you do. But you only get to it after, a bit of an excursion, right? As you can see, you go through this sequence of numbers, and then you get to halt. All right? So the 5-state Busy Beaver champion very slowly, which we like, slowly verifies this fact. Okay? So it just keeps computing g of x, halts when it gets to the halt state, and it uses about x squared steps for each x. Okay, and by the way, if you're wondering, the 6-state Busy Beaver champion does something very similar to that. It just keeps iterating some function until it reaches a halt state, but in that case, the function involves exponentiation, and that is how you can get much, much larger values very quickly. Yeah? Oh, well, because we're talking about Busy Beaver of 5. I mean, to actually write down the machine and interpret it, that would be a very long and very boring digression. Okay, but you can look up the machine if you want, there's a nice survey article by Pascal Michel where he actually shows you the machine. He decompiles it. I actually have a picture. Here is a picture of the 1s and 0s on the tape as you run that 5-state Busy Beaver champion, okay? And so it just keeps iterating that G and getting to the bigger values of X. Yeah? No, it was just, it was discovered by doing a search over Turing machines. And then later people interpreted what the machine was doing in terms of that function. And well, maybe there's another one, okay? But this one, it's like each of these parabola, each of these parabolas you can think of as, as doing that for another value of x. Okay, so it's a very natural interpretation. Okay, now some of you, might be reminded at this point of a very famous or infamous problem in math called the Collatz conjecture. Okay, and as you can see from the famous XKCD cartoon, the Collatz conjecture states that if you pick any integer, and if it's even, divide by 2, and if it's odd, multiply it by 3 and add 1, and you keep repeating that procedure long enough, eventually your friends will stop calling to see if you want to hang out. Okay? Actually, it says eventually you will reach 1. Okay? And this remains an open problem. Paul Erdős said mathematics is not yet. But I'd like to say, the Collatz conjecture has some claim to being possibly the most elementary of all open math problems. Okay, so it has a claim in the sense that empirically it's the open problem that I can explain to the youngest children. Right? I can easily explain this problem to 5-year-olds, for example. Okay. But the Busy Beaver game gives us a different sense, in which empirically, this kind of question seems like perhaps the simplest kind of extremely hard math problem that it is possible to invent, right? Like as you just iterate over Turing machines, right? These are the first extremely hard problems that you find. Right? They are problems about the halting of Turing machines that basically test Collatz-like statements. Okay, so now what about Busy Beaver of 6? Will it ever be known? Okay, well, the BB Challenge collaboration made another interesting discovery. Okay, they found that there is a 6-state Turing machine which halts if and only if, starting from x equals 8, when you iterate this function, so g of x is 3x over 2 if x is even, or 3x minus 1 over 2 is odd, and you just look at all the numbers that you've generated so far, then at any point you ever have more than twice as many odd as even numbers. Okay, if that's ever true, you halt, otherwise you run forever. Okay, so what do you think? Run forever or halt? Well, of course you can code this up, you can try it, and what you find, maybe not shockingly, is that the number of odds and even x's remains pretty balanced. Okay, and it looks like a fluctuation make the number of odds twice the number of evens seems rather unlikely, more and more vanishingly unlikely as you go to more and more numbers. Okay, but to prove such a statement seems kind of like having to prove the Collatz conjecture itself, right? And so what we learn is that Busy Beaver of 6 cannot be known until someone solves this Collatz-like statement, and possibly 1,000 other Collatz-like statements, which are all hiding in the 6-state Turing machines. Okay, so I would like to make a personal prediction, which is that if BB of 6 is ever known, we will need the help of our AI friends. Okay, I don't think that humans are going to determine this number. Okay, so now we can ask, is there an ultimate limit of the knowability of this Busy Beaver function? And it turns out that there is. Okay, so here is just an easy corollary of Gödel's incompleteness theorem. Okay, I claim that any consistent formal system can prove or determine at most finitely many values of this function. Okay, why is that? Well, let me just show you very concretely and constructively why. Okay, suppose that you build a Turing machine, so a program M that has n states, and what it does is it lists all the possible theorems in F, one by one, just applying the inference rules in every possible way, and it halts if and only if it ever finds a contradiction. Let's say a proof of 0 equals 1. Okay, so now let's suppose that our formal system F proves the value of Busy Beaver of n. So like it proves that Busy Beaver of n is equal to k, for some integer k. Okay, well then at that point F would also prove whether M halts, right? Because M is an n-state machine, and so F, in F I can just give an execution trace of M where I run it for k steps. I check whether M has halted by then. If it hasn't, then I know that it runs forever. But if it runs forever, then I know that F is consistent. And therefore, F has proven its own consistency. Okay? And Gödel tells us that that's a no-no. Okay? So this was, an argument that tells us that there is some n at which the value of Busy Beaver of n stops being determinable by, the axioms of math. It doesn't tell us which value. Okay, so a decade ago, I got curious about that. Like, is this value, is it more like 10 or is it more like 10 billion? Okay, like, let's talk price here. Okay, so I got actually a student, I was then at MIT, named Adam Yedidia, and he and I did a project which was, as much software engineering as it was math, to try to build a Turing machine with as few states as possible that does this. Okay, and we managed to get down to 8,000 states. Okay, so we proved that the value of Busy Beaver of 8,000 is independent of the usual axioms of set theory, of ZFC, assuming some consistency statement that's a little stronger than the consistency of ZFC. Okay, for this, we used work by Harvey Friedman, okay, but in logic, but the most important idea that we had to get down the number of states was something that we called introspective encoding. Okay, so this meant that instead of just directly trying to enumerate all the theorems, we first wrote onto the Turing machine tape a program to enumerate the theorems written in some higher level language, and then we interpreted that program. Okay, so we had another part of the Turing machine that runs this program that's on the tape. So it's like a multi-stage rocket. okay? And, you know, and that actually saves you a lot of states when you do that, right? You can even do multiple layers of it, okay? Without that, we would have needed more like 100,000 or 1,000,000 states. Okay, and since then, Stefan O'Rear and Johann Riebel have managed to improve our result to show that Busy Beaver of 745 is independent of the axioms of set theory. Well, good question. Yeah, I was, but it's still nice to know. So in fact, I would actually ask whether it's even much smaller than that. Okay, so here's my question. Like, what about Busy Beaver of 8? Is that one already independent of ZFC? I would kind of like to know, right? We've got 2 orders of magnitude now between, you know, Busy Beaver of 5, which we know, and Busy Beaver of 745, which we know that in some sense we can't know, at least, you know, within the resources of ZFC. Okay, so like how far do you have to go before you know, reach the abyss? Okay, but now in the remaining, so this was all a story about computability and provability, about, you know, which infinite questions sort of can or cannot be reduced to checking a finite proof, or, you know, doing a finite calculation. Okay, but in modern computer science, you know, starting in the 50s and 60s, when people started to use actual computers to do things, they realized that very often that's not the most important question at all, right? Very often the questions we care about are ones that we know that we can reduce to some finite calculation. The problem is that all the obvious ways of doing that would give us a calculation that would take longer than the age of the universe. Okay, so now again, we want to talk price. We want to talk numbers, right? We want to say, you know, there is finite and then there is finite, right? There is, you know, let's say 1,000,000 lines or 1,000,000 steps, you know, which we can check with our computers, and then there is a Googleplex steps, okay, which is finite, you know, in the formal sense, but which does not fit within, you know, the observable universe. Okay, so we want a sort of conceptual vocabulary to distinguish those cases. Okay, so, you know, even when finite proofs exist, they could take longer than the age of the universe to write down, and but it's more than that, because it's even when there are short proofs. You know, even when some theorem has a proof that's, let's say, 1,000,000 bits long, right? How many different strings are there of 1,000,000 bits? Well, there's 2 to the 1,000,000 power. Okay, that's way more than the number of subatomic particles, you know, in the observable universe, which is merely 10 to the 85 or so. Okay, so because of exponentiality, you know, even short proofs could take longer than the age of the universe to find. Okay, and this issue was actually very, very lucidly noticed by our old friend Gödel. Okay, in a letter that he wrote to John von Neumann in 1956, okay, which was lost for decades and then, you know, rediscovered. But von Neumann at the time was dying of cancer in the hospital. But Gödel wrote him this letter where he said, you know, my dear Mr. von Neumann, I hear that you're recovering. He wasn't, but, you know, since you are, let me take the liberty to trouble you with a mathematical question. Okay, and he then asked, like, what we would immediately recognize today as the P versus NP problem. Okay, so he basically asks, look, suppose that I'm given a theorem in some formal system, and I just want to know, is there a proof with of at most n symbols? Okay, or if there is such a proof, I want to find it. Okay, then he says, clearly there is a finite procedure to do that. I can just enumerate every possible string of n symbols or fewer. You know, that takes finite time, but that's not the real question, he says. Okay, the real question is there a procedure that would use a number of steps that scales only modestly, like n? Okay, he says, for example, like linearly in n, or even only quadratically in n, right? Today in computer science, we say polynomially with n. He also asked about primality testing and whether that's in P. Yeah, in the same letter. Okay, but he says, okay, if a procedure existed to find proof of size n in only n or n squared steps, whenever such proofs existed, that would have consequences of the greatest magnitude. It would mean that the mental effort of the mathematician could be completely replaced by machine. And then he adds in a footnote, apart from the postulation of axioms. Okay, so basically he's saying you would simply have to choose an n so large that either there's a proof of length n, or else maybe you don't even care anymore, right? Proof's just too long. Okay, but in any case, finding proofs would then be not only somewhat harder than just checking the proofs, than writing them down. Okay, so this leads us to P versus NP. Okay, which is here it is in the Simpsons episode. Okay, here's P, here's NP. So basically, I'm not going to go through defining all these things, but P is polynomial time. It's the class of all the problems that we can solve with a standard digital computer using a number of steps that grows like the size of the input raised to some fixed power, or in other words, polynomially. Okay, that actually includes most of what we do with our computers on a day-to-day basis, basic arithmetic, even more interesting things like solving linear systems of equations, finding matchings in graphs. Okay, NP stands for non-deterministic polynomial time. Note that it isn't not polynomial. Okay, NP is the class of all the problems where if the answer is yes, then there is a short proof that it's yes, and that proof can be efficiently checked. Okay, so a canonical example of a problem in NP is factoring, right? Like I give you a huge composite number and I ask you, for example, does it have a prime factor ending in 3? Okay, if it might be very, very hard to solve that problem. Okay, in fact, the security of most of the encryption that protects the internet is based on the belief, which might or might not be true, that this kind of problem is hard, right? That, for numbers of many thousands of digits, that it could take longer than the age of the universe. Okay, but certainly if someone wanted to prove to you that the answer was yes, then they could just show you the prime factorization, right? And with your computer, it would be easy enough to multiply the numbers. We also know of fast methods for checking that numbers are prime. Okay, now at the top of NP are the so-called NP complete problems, and these are in some sense the hardest problems in NP. They're the NP problems that if you could solve them in polynomial time, then you could, any one of them, then you could translate that into an efficient algorithm to solve any NP problem. Okay? The great discovery of the early 1970s that really started theoretical computer science as we know it today was that not just one or two, but hundreds of the problems that people most care about. So, satisfiability, fitting suitcases into the trunk of your car, scheduling flights for an airline, Sudoku, Super Mario, as well as various less useful things like industrial optimization and so forth. Okay, these are all NP complete, and in fact, whenever you have a problem with a bunch of sort of constraints that might or might not conflict with each other, relating a bunch of different variables that could be set independently, these problems tend to be NP complete unless they have a very good reason not to be. Okay, so then there's P, NP complete, and then there's this no man's land, right? There is this stuff that, as far as we know, is somewhere in the middle, like factoring, things that are very useful for modern cryptography, also determining if two graphs are isomorphic. Okay, and now the famous open problem is just, is P equal to NP? So in other words, whenever you could efficiently check a solution, then can you also efficiently find one? Okay, or we could equivalently ask, is any NP complete problem solvable in polynomial time? Okay, I think that this has, I know that I'm sure there are people in this room who would fight me, okay, but I think that this has some claim to being the greatest unsolved math problem. Okay, and the argument for that is simply that depending on how this question was resolved, like if P equaled NP by an algorithm that was very fast in practice, and you showed that, then you would not merely solve this problem. Okay, you would show that you can then program your computer to solve pretty much all of the other math problems. Okay, ask your computer, is there a proof of the Riemann hypothesis in ZFC of 1 billion bulls or fewer? okay, and so forth. So it's sort of, it is a extremely hard math problem about, the possibilities of mathematical knowledge itself. Okay, and now there's another case that people make for the importance of the P versus NP problem. And I actually heard people make this argument like 20 or 25 years ago. Okay, they said, look, here is the real reason why P versus NP is such a profound problem. Okay, they said, suppose that P equaled NP and that you could really efficiently solve, every efficiently checkable problem. Okay, well then what you could do is just find a neural net or some machine learning model that would just optimally predict, let's say, all of the text on the internet, right? And then, very plausibly, if you had found that, like, you would need to have unraveled many of the secrets of intelligence itself, right? Like, how would you optimally compress the whole internet except by sort of understanding the world that had given rise to it, right? And maybe that would then solve AI, right? And I regarded this as a very interesting intellectual point, right? As a sort of, underscoring the almost metaphysical significance of P versus NP, okay? But, you probably all know what happened, which was that a company called OpenAI came along and said, hold my beer, right? Let's actually do that, okay? Even though, presumably, P doesn't equal NP, let's just do the best that we can, okay? Let's train a neural net on all the text on the internet, use, gradient descent to try to find, one that's as optimal as we can, even if it's not exactly optimal, and let's see, if it works at, writing poems or solving math problems, okay? And the answer is, it does work, not perfectly, but I think better than almost anyone on earth would have predicted a decade ago, okay? And so now here we are, okay? So this is, by the way, Ilya Sutskever, co-founder of OpenAI, and he actually hired me. I went on leave from UT Austin to work at OpenAI for 2 years, ending this past summer in their safety and alignment team, which unfortunately no longer exists. Okay. But that's a different talk, okay? In this talk, I want to say a few words about quantum computing, which actually is the thing that I've spent most of my career working on, okay? And, as soon as you ask, like, what is efficiently computable, what is computable in polynomial time, as we do with the P versus NP question, then, before long, you notice, wait a minute, the laws of physics might really be relevant here. Right? Not just in the abstract sense that they were with computability, that, okay, if someone could build that Xeno computer, then that would change computability, but they can't, right? But, it might be that the real actual laws of physics might change what is computable in polynomial time, okay? And, this observation was first made in the late 70s and the early 80s by a few physicists like Richard Feynman and David Deutsch. And they pointed in particular to quantum mechanics, okay? And they said, what quantum mechanics has told us since, 1926 is that if you want to describe the state of, let's say, n particles, each of which could be in one of two configurations, so what we call the quantum version of a bit or a qubit, okay, then it is not enough to just describe the state of each of those particles separately from all the others. Instead, I need a number of parameters that grows like 2 to the n, okay? An exponential number of parameters, which are called amplitudes. Okay, I need one amplitude for every possible configuration of all n of these bits, right? And these amplitudes are related to probabilities, but they're not probabilities. They're actually complex numbers. To simulate let's say the physics of some, chemical reaction or some material, and to actually make predictions, I may need to keep track of this exponential number of parameters, okay? And on its face, this seems exponentially hard to simulate on a classical computer for a somewhat different reason than why the NP-complete problems seem hard, okay, but related. Right? You again have these exponentially large sums to keep track of. And so that led to their idea, which was if nature is handing us this computational lemon being so hard to simulate, then why don't we make lemonade out of it, right? Why don't we build computers that would take advantage of the same principle, that could have these superposition states with these exponential number of amplitudes. Of course, they then immediately face the question, well, supposing that you built such a machine, what would it be good for? And they only really knew one answer to that question, which was it would be good for simulating quantum mechanics itself. Now, I think, more than 40 years later, that's still the most important application that we know. Okay, although there are now many, many large companies and startup companies that have a great interest in muddying that point. Okay, but so in particular, like 30 years ago, a certain narrative took hold about quantum computers and how they would work. Okay, and it just said, well, unlike a classical computer that has to try a possible answer one by one, a quantum computer could just try them all in parallel, in superposition, and that's obviously much faster, right? And that sounded great. That's what everyone wanted to hear. Okay, the only problem with it is it's not really true. Okay, I mean, yes, with a quantum computer, you can create a superposition over all the answers, even exponentially many of them. That's even an easy thing to do. Okay, the trouble is, for a computer to be useful, at some point you have to look, you have to measure, you have to get an output. Okay, and if you just measured the state of your quantum computer, in an equal superposition of the answers, not having done anything else, the rules of quantum mechanics are unequivocal that all you'll see is a random answer. Right? If you just wanted a random answer, you should have flipped a coin a bunch of times, right? Saved the billions of dollars. Okay? So the only hope of getting an advantage from a quantum computer is to exploit the way that these amplitudes, being complex numbers, work differently from probabilities. Okay, so with every algorithm for a quantum computer, the idea is to try to exploit interference. Okay, which means like for each wrong answer, I'm going to have it'll have an amplitude that's a sum of a bunch of contributions, right? And some of those contributions will be positive and some will be negative, so they'll cancel each other out. Whereas for the right answer, I want all the different contributions to its amplitude to be pointing in the same way, right? If I can arrange that, then when I look, I'll see the right answer with a high probability, okay? The hard part is I have to do that even though I don't know in advance which answer is the right one. If I already knew, what would be the point? Okay, and I've got to do this faster than the fastest classical algorithm. Okay, so this is a really bizarre hammer that nature is giving us. I think it is weirder than any science fiction writer would have had the imagination to invent. Okay, but then it's our job to figure out, well, what nails can it hit? What's it good for? Okay, so maybe many of you know this story, but 30 years ago, this guy, Peter Shor, discovered that there are efficient quantum algorithms for at least a few of these NP problems that seem to be, well, or at least that we do not know to be in P. Okay, most famously factoring and discrete log, which so happen to be the problems on which we base most of the security of the modern internet. Okay, so he says, if you build a quantum computer, you can break all that stuff. Maybe the most fun thing you could do is you could steal maybe $100 billion worth of Satoshi's bitcoins. Okay, not that I advise that. But as you also see from this picture, today we do not know if even a quantum computer would be able to solve the NP-complete problems in polynomial time. Okay, most of us can ensure that they couldn't. Okay, so quantum computers seem to change the limits of what is efficiently computable, and therefore what mathematical statements are knowable by us, in this world. Okay, but they only change it in a sort of slight and subtle way, right? Letting us solve some problems and not others. Okay, and so I know many people would like to know, well, where are we now with building quantum computers? So in December of last year, the group at Google in Santa Barbara announced that they built a chip called Willow with 103 superconducting qubits, and that using this chip, they got some new mathematical information from the universe that we would not know how to get classically, with any known algorithm. with the largest currently existing supercomputers in less than 10 to the 25 years, okay, which is much, much longer than there's been since the Big Bang. So you might ask me, what is that information? Well, it basically says this sequence of 103-bit strings are statistically likely outputs of such and such random sequence of quantum operations. So, you know, now I didn't promise you that it was going to be interesting or useful information, okay? In fact, you know, it is information that we don't even know how to directly check is correct in less than 10 to the 25 years. So, you know, that is a problem. Shor's algorithm would eventually fix that, but that seems to require an error-corrected quantum computer, which we don't yet have. You know, we're making progress. Okay, so you know, you could ask, is there anything beyond quantum computing? And you know, there's this statement called the quantum extended Church-Turing thesis, which says that all physical systems can be simulated efficiently, meaning with polynomial overhead, on a quantum computer. Okay, so this would say, once we get to quantum computing, this is just the end of the line. This is the right answer for what is efficiently computable in nature. Okay, but is that true or false? Well, you know, it is some empirical claim about the laws of physics. Okay, if it were false, then even more mathematical truth could be knowable to us. So what is the status of this thesis? Okay, so there's, you know, fun ideas that people have had. I think my favorite is the relativity computer. You know, well, why does quantum mechanics get all the love, right? So the relativity computer is very simple. You start your computer working on some very hard problem, you know, maybe an NP-complete one, then you get on a spaceship, you accelerate to near the speed of light, you return to Earth. Now, billions of years have passed in Earth's time. All your friends are long dead. Civilization is dust and ashes. But if you can find your computer in the rubble and it's still running, then you can get the answer to your hard problem. Okay? So why doesn't anyone try it? Well, you know, there are some issues with energy, right? You know, to get enough fuel to power this spaceship, it seems like maybe you would again need to create a black hole. Closed timelike curves, you know, again, Gödel himself was one of the first to think about solutions to general relativity that involve time travel to the past. Okay, and you might say, well, if time travel to the past existed, you know, then we'd be good to go. We could just keep reusing the same time over and over and solve super hard problems that way. I don't think that really works because it ignores the need for causal consistency. Like the grandfather paradox. What happens when you go back? You kill your own grandfather, and then, you know, you're not born, and therefore you don't kill your grandfather. So what's going on? So David Deutsch, same guy from quantum computing, in 1991 proposed a quantum mechanical resolution of the grandfather paradox. He basically said a closed timelike curve, if it existed, would just be some region of the universe where nature is forced to find a quantum state that is left invariant by whatever happens around that curve. Okay, and then he proved a theorem that says that in finite dimensions, at least one such fixed point always exists. So, for example, the resolution of the grandfather paradox would simply be, you are born with probability half. If you are born, then you go back in time and you kill your grandfather. Therefore, you are born with probability half. You know, everything is consistent, there's no paradox. Okay? Okay, but Deutsch also pointed out that just enforcing nature to find a fixed point of some given evolution, you know, we could again be forcing nature to solve a very hard computational problem, right? Just like in the science fiction movies where someone like goes back in time and tells Shakespeare what plays he's going to write, right? And Shakespeare says, oh, thank you, you saved me a lot of effort. And so, you know, everything's consistent, but, you know, Hamlet somehow popped into the universe without anyone writing it. So just how hard of a problem can we solve? In 2009, John Watrous and I had a paper where we showed that you could solve exactly the problems in the class P space, which is everything you can do with a polynomial amount of memory, possibly an exponential amount of time. And we have a paper from last year that says that if you could send an unbounded number of bits back in time, then, you know, in some way of formalizing that, you can actually solve the halting problem. Okay. So, all right, so that brings us the last thing, quantum gravity. Roger Penrose believed, believes famously that the union of quantum mechanics with general relativity is going to lead to literal Turing uncomputability in our world. He also believes that that follows from an argument based on Gödel's incompleteness theorem, and that it underpins human consciousness. Suffice it to say that each individual step of that is rejected by most of us. Okay, but modern work in quantum gravity, specifically in the ADS-CFT correspondence, which came out of string theory, hints at, possibly the exact opposite statement, that even a quantum theory of gravity that lives in what's called a bulk spacetime is dual to, or can be mapped to, some isomorphic theory that just lives on the boundary of that spacetime, different number of dimensions, that boundary theory is just an ordinary quantum field theory called a conformal field theory, so presumably is computable. So if this is true, it suggests that even quantum gravity should ultimately be computable. Okay, but there is recent work by my former students, Adam Boland and Bill Pfefferman, and my former advisor, Umesh Vazirani, okay, where they show that the dictionary, the mapping between the bulk states and the boundary states, computing that seems to involve solving problems that are hard even for quantum computers. So does that mean that the quantum extended Church-Turing thesis is false? Does that mean that we can actually do something beyond what a quantum computer can do if ADS-CFT is the right description of quantum gravity? Well, I don't know, because I don't know how to project myself onto the boundary of the universe. Okay, like I don't know, even as a thought experiment, what does that mean? But ultimately these are questions for physics. So to summarize, one way to describe math is that we are finite beings trying to apprehend the infinite. Okay, as like fluffy as that statement sounds, the Busy Beaver function accomplishes the incredible feat of actually quantifying it. But even the finite can exceed the scope of the cosmos, and that is where we need physics and computational complexity theory. Quantum computers look like they're already slightly expanding the scope of what mathematical statements we can learn, and hopefully we'll do more in the future. And can we know even more than what a quantum computer can tell us? Well, that depends on what the ultimate laws of physics are. All right, thanks for listening.